In this video, I will discuss the specimen geometry that we need for our EBSD measurements. In general, the sample needs to be mounted at a surface tilt of 70 degrees to allow the EBSD signals or the diffracted signal to escape from the sample and reach our EBSD detector. You can do that by applying a full 70-degree stage tilt or a partial pre-tilt. For example, when the stage doesn't allow you to tilt full 70 degrees, you can mount your sample at a holder at perhaps 45 degrees, like on some microscopes, and add 25-degree additional stage tilt to reach the 70 degrees that we want. Or you can use a full 70-degree pre-tilted holder, but be a little bit careful with that you have to make sure that the whole stage can go low enough that the EBSD can be safely inserted. This is not possible on all microscopes. In general, you have to be very careful with mounting the sample and make sure to mount it very firmly with a clamp or a very solid glue, and try to avoid tape or carbon pads with thicker glue layers, because the moment you tilt your sample, the gravity will start pulling, and when the sample is not mounted very firmly, it will move and cause drift in your EBSD measurements. Here's a geometry when you can tilt the stage completely to 70 degrees. So you mount your sample horizontal, tilt the stage to 70 degrees, and then mount your sample or position the sample at the working distance that you want to use. One thing to keep in mind when you use this geometry is that the XY axis of the stage may also tilt to 70 degrees. And that means that the Y movement of your stage actually becomes a vertical movement that brings your sample closer to the pole piece or further down away from the pole piece. So be aware when you make any large movements of your sample, switch on the chamber scope and see that what you're doing is actually safe. Then you can also do a partial pre-tilt, and in this example there's the stage, and the edge of the stage here has a 45-degree pre-tilted angle. We can mount the sample on that side, tilt the entire stage another 25 degrees, and then do our EBSD measurements. Finally, we can go to full pre-tilt. So I have a taller base here, 70-degree pre-tilt, there's the sample, and the advantage of this is that the X and Y planes stay horizontal, so the movement of the sample is a little bit easier. But it also gives us a little bit more flexibility for those chamber configurations where the EBSD detector cannot be mounted along the stage tilt axis direction. So when this EBSD detector is mounted at a different angle at the chamber, you have to use a 70-degree pre-tilted holder, rotate your sample towards the EBSD detector, and then you can do your measurements. But you have to be careful. You have to apply an image rotation to ensure that the horizontal beam movement is also horizontal on the sample. So when you are not in the stage tilt axis and you rotate away a little bit, you have to apply a matching image rotation. Because the sample is so steeply tilted, we have to apply some image adjustments. And one of these is the dynamic focus. And we need to use that because the sample surface is tilted over a range of working distances. Normally in the SCM, you would have your sample horizontal, you focus at a certain working distance, and the entire image is in focus. But when you tilt the sample 70 degrees for EBSD, you can focus on the center part of the image, but you will see that the top and bottom of the image are out of focus because they are physically at a different working distance. And in the example here, the working distance range for this image is about 300 micron, and you get a distinct out of focus view at the top and bottom of the image. Now, you can do this dynamic focus by continuously changing the focal distance of the microscope onto the SCM image. And you do that with the dynamic focus function on the microscope. And to set that up, first thing we have to do is switch off the dynamic focus and focus your image on the horizontal center line of the picture on the microscope. Once you've done that, you switch on the dynamic focus function, and then you can adjust it for the entire image to make sure that the whole picture is nicely in focus, and we will get a proper image and detail from top to bottom. Please note that this dynamic focus needs to be set up on the microscope side. This is not something that we do on the Apex software. Another image adjustment that we have to apply is the image tilt correction. Because the image, again, the sample is so steeply tilted, the microscope only sees it in a compressed form, and we need to stretch that to get the proper aspect ratio of all our microstructure measurements. And this tilt correction is done automatically within the Apex software. And there you have a choice. You can either choose to set it up on a tilt corrected image so that your original image is already shown in the proper aspect ratio, or you can set it up without tilt correction on the underlying SCM image, and when you use that, Apex will stretch the image to the proper aspect ratio before you start your EBSD measurement. Now, something important you have to remember is that you should not use the tilt correction function on the microscope, because Apex doesn't know when that has been switched on, and it will do it again. So when you switch on the tilt correction on the microscope, you will get a double correction to be applied, and the aspect ratio in your image will be wrong. Also, do not use the image rotation function on the microscope unless your system geometry specifically requires that. Because if you rotate a little bit and the horizontal direction of your SCM image is not parallel to the tilt axis on your sample, so that the electrons go obliquely over your sample over the tilt, then everything will be distorted very badly. Now, where to find this tilt correction in Apex? If you go to the top left here where you kept your SCM image, you can go to the Collect Image parameters, and here we have the tilt correction checkbox. So you can check that, and then the SCM image will be read in, and we take the center 1/3 from the image that is shown on the microscope and stretch it to the proper aspect ratio. And then our EBSD measurement will match that image, and you can just see what you get before you start the measurement. Very convenient, but it also limits the size of the scan that you can collect. You can also collect a map without tilt correction. You can simply take away this check mark. It doesn't mean that now your measurement will be distorted, because Apex knows that the image is not corrected yet, and when you will start your measurement, the image will be stretched to show the proper aspect ratio. So when I do that, I hit the collect button over here, and then the image gets stretched to the proper aspect ratio, and you can see this is about 3 times larger than the field of view we saw earlier. So it allows you to get a much larger mapping area. And then on this image is where we collect our EBSD data, and that we get just again a good tilt corrected image that has the proper aspect ratio of the microstructure. So for the EBSD data collection itself, it doesn't matter if you switch this tilt correction in Apex on or off, the software will automatically apply the appropriate aspect ratio corrections. It's just that when you do not use the tilt correction, it will allow you a 3 times larger field of view at the same SCM magnification, which can be very helpful, for example, if you are measuring a thin coating on some substrate and you want as large as possible field of view. Now, the other thing for EBSD measurements is the reference frame. We have mounted the sample, we mount the sample at 70-degree tilt, and any measurements that we collect are with respect to a reference. And the reference frame that we use for EBSD is this, X, Y, Z, or 100, 010, 001. And in the literature, you may find different descriptions. And typically here at the bottom you can see what they correspond to. So axis 1, 2, 3, or XYZ, or 100, or 10, or 1, etc. That is fixed. So we mount a sample like this in a microscope, 70-degree tilt, and this is our reference orientation with respect to what we define our measurements. Now, a peculiarity of the microscope is that we will have some rotations here. In most cases, the microscope imaging will start on the side of the chamber where the SE detector is mounted. So when we are looking at the sample from the door of the microscope, the EBSD is mounted on the left, SE detector is mounted on the left, which means that the scan will start on the left. And when you look at your SEM image, it will start at the top. So this will be like a 90-degree rotation between how the sample is mounted and how it is displayed in your SEM image. When we tilt the sample, this becomes even more extreme because the scanning still starts on the left side where the SE detector or the EBSD detector also is mounted, which means that it starts at the bottom of the sample, the furthest away from the pole piece. And in your SEM image or your EBSD map area, that is the top of your image. So the picture that you see in your SEM software and also in the Apex software is upside down with respect to the physical sample, how it's mounted in the microscope. So if I take a picture, that's what you get. So if you have a sample that requires a specific mounting because you have a very special direction that you need to measure, make sure that you measure it or you mount it so that you can recognize the feature of interest on your SEM image and the EBSD maps. Now, this coordinate system that we use is always with respect to the sample surface. So if I insert the EBSD detector, you can see here axis 1, 2, 3, where axis 1 and 2 are in the plane of the sample, axis 3 is perpendicular to it. And here we have an IPF map, and in the legend of the IPF map in the analysis software, you will see the axis indicated. So axis 1 down means the physical axis in the plane of the sample downwards, how you have mounted your sample in the microscope. And axis 2 to the right is the physical axis to the right. Axis 3 is the sample normal, and that is perpendicular to the screen. The same geometry is indicated in the pole figures, where we have axis 1 and axis 2. This display would match with how the sample is mounted in the microscope. However, when we want to display it with respect to the image, how we see it on the microscope user interface and in Apex, which means upside down, we also have to rotate the coordinate system. So axis 1 up, axis 2 is to the left, and 3 is perpendicular, and that is also indicated in the legend. So if you look at this IPF map, you wouldn't see a difference because the viewing direction is the same for both, but axis 1 and 2 are rotated 180 degrees. So again, when you need to see a very specific direction in your material, be aware with the scanning direction and how that affects your data. This geometry is indicated by the specimen coordinate system in the software. This will be set up when the system is installed, and on most microscopes, setting number 2 is correct, and you can just check that by mounting a feature with a very recognizable top-down. So let's say a coin, you mount a coin, look at the SEM image, and you can see with which setting that corresponds. And again, in most cases, it will correspond to setting number 2. When this is set up, you don't have to change it. It's just fixed with respect to your microscope geometry.